Okay, I welcome you back to my video presentation. I am C. Ashok Kumar, Professor, Department of EEE, and my course name is Electronic Device and Circuits. And this is a Unit 2. Title of the Unit 2 is Diode Applications, and the topic for this today lecture is full wave rectifier. I will be discussing about operation and derivation of parameters. And overview will be going on like this. First, I will be discussing about the full wave rectifier operation, and then I will be deriving all the parameters related with the full wave rectifier like ripple factor, efficiency, and transformer utilization factor, and so on. Okay, and finally I will be recapping the things whatever I discussed. And the textbooks referred, three textbooks I kept. One is EDC, Electron Device and Circuits by Jacob Millman, and second one is Electron Device and Circuit Theory by Robert Polistad and Lewis Neshelski, and third one is Electron Device and Circuits by Salivahanan and Suresh Kumar. So first topic is about the full wave rectifier operation. So in the last class we discussed about the half wave rectifier, and now we are discussing about the full wave rectifier. So the full wave rectifier circuit diagram, as you can see here, this is the circuit diagram, and this is the transformer here. As you can see here, the transformer is a center tap transformer, not a conventional center tap transformer. I will be discussing about the features of center tap. So as you can see here, two diodes we are utilizing. One is diode D1, second one is the diode D2, and as you can see here, the load is kept here, across which we need to measure the output voltage. Okay, so what do you mean by center tap transformer? As you can see here, suppose in our lab the center tap transformer specifications will be like this: 909. That means, as you can see here, the upper half 9 volts will be getting, and the lower half of the secondary winding also will be getting 9 volts. See here, both are out of phase with each other. Okay, suppose in the upper half, if you get 9 volts, the lower half will be getting minus 9 volts. Magnitude is same, but they are out of phase with each other. Two halves will be there, upper half and lower half. 909 transformer means upper half will be getting 9 volts and lower half also will be getting 9 volts, but they are opposite with phase. Okay, suppose if it is 9 volts, here the lower half must be minus 9 volts, like that. Okay, so that is called as a center tap transformer. So this is the primary winding and this is the secondary winding, where you can see two halves, okay, divided equally, upper half and lower half. So here the input voltage here will be the AC input voltage. The rectification, you know about rectification property, the conversion of AC signal to a DC signal. Okay, conversion of AC current to direct current, that is a rectification. That's why here we need to give the AC input voltage. As you can see here, Vin. Vin is a AC input voltage. AC input voltage means household purposes 220 volts and some 60 Hz frequency will be there. This is the AC input voltage. So now let us go for the operation, how the operation goes on. Okay, so here the Vin, it is a AC signal, that's why I represented like this. So this is a voltage versus the time scale, angle of conduction, that is omega t. And here, as you can see here, this first half, positive half, the cycle, the duration will be from 0 to pi. Omega t is in between 0 to pi, that we will be calling it as a positive half cycle. Whenever omega t is in between pi and this is 2 pi, pi and 2 pi, so this is the negative half cycle. Okay, so when omega t is in between 0 to pi, it is positive half cycle. Whenever omega t is in between pi to 2 pi, it is negative half cycle. And Vm is the peak value of this AC voltage, Vm, as you can see here. Okay, so now let us go for the operation. During the positive half cycle, what happens? During the positive half cycle means whenever omega t is in between 0 to pi. So here I am taking this terminals as A and this one as a B, right? Whenever input voltage is in the positive half cycle, whenever omega t is in between 0 to pi. Okay. So this A becomes more positive when compared with B. A becomes more positive when compared with B. So here plus sign I am keeping and here a minus sign I am keeping, right? A is more positive when compared with B during the positive half cycle, right? So then what happens to the diodes? Assume that we are assuming that the diodes are idle. Idle means what is the property of ideal property of a diode? Whenever it is forward bias, it must offer zero resistance. Whenever it is under reverse bias, it must offer infinite resistance, right? So that is the ideal property of a diode. We are assuming our diodes to be ideal one, right? So this is a positive and this is a negative. So as you can see here, this is a anode and this is a cathode of the diode. Anode is more positive when compared with cathode. That's why this diode will be forward bias. Whenever this diode is forward bias, it acts like a short circuit. That means it is offering zero resistance and a current will be flown through the diode like this in this direction. So through the load resistance RL, and as you can see here, this is a ground terminal because it is center tap. This one is a ground terminal, okay, common terminal. So whenever this diode D1 is forward bias, a current will be flown and the current direction will be like this, that will be flown through the load resistance RL in order to reach the ground, common terminal. So whenever current is flowing here, a voltage will be developed across this load resistance RL, that we will be calling it as V0. Okay. So a voltage will be developed across RL due to the conduction of diode D1 during the positive half cycle. And that's why here V0 can be represented like this. So V0 is equal to the current into RL. You will be getting V0. V0, once again, it is a sinusoidal signal, right? So V0. So during the negative half cycle, let us see what happens. So here once again same terminals A and B. During the negative half cycle, this B becomes positive when compared with A. That means here plus sign will be there and here minus sign we can take, right? So if you observe this diode D1, as you can see here, a negative voltage will be there for the anode. That's why this will be reverse bias. And what about the status of diode D2? So this diode D2, as you can see here, B is more positive. That's why here anode is more positive when compared with cathode. That's why this diode D2 will be forward bias. Forward bias means it acts like a short circuit. It is offering zero resistance. So once again here a current will be developed through this diode D2. Okay, let it be I of t. So the current will be flown in this direction through the load resistance RL, once again in order to reach the ground. Okay, so diode D2 is conducted during the negative half cycle whenever omega t is in between pi to 2 pi. So the diode D2 is conducted through which a current will be flown in this direction through the load resistance RL in order to reach the ground. So a current is flown through the load resistance RL. Once again a voltage will be developed. We need to call it as a V0. So that's why here during the negative half cycle also of the input voltage also, here we are able to observe an output voltage. Whereas, so here P means instead of P we can write it as 2 pi, pi and 2 pi. This is a positive half cycle, the voltage is developed, and also during the negative half cycle also the voltage will be developed. Where in the half wave rectifier we did not observe this one. During the negative half cycle the output voltage will be equal to 0. Because we are using only one diode, right? So this is about the operation of the full wave rectifier. So full wave rectifier, what is happening here? Both in the positive half cycle as well as negative half cycle, the voltage will be developed. Output voltage is defined. Okay. So that's why here we can write the output voltage equation like this for our analysis sake, for our derivation of parameters. I am writing the equation of output voltage. So whenever omega t is in between 0 to pi, so this cycle, so we are able to develop an output voltage. So that's why here I am writing output voltage equation like this. V0 of t is equal to Vm sin omega t. Okay. So similarly here, in the second half cycle, negative half cycle, whenever omega t is in between pi to 2 pi to 2 pi, so same voltage is developed. That's why here I am writing same equation here. V naught of t is equal to, so I am writing here V naught of t is equal to same Vm sin omega t. Okay. So finally I will be concluding here. During the positive half cycle, as you can see here, when omega t is in between 0 and pi, V naught of t is equal to Vm sin omega t. Whenever omega t is in between pi to 2 pi, V naught of t is equal to same Vm sin omega t. Okay. So this is about the operation, and also I wrote the output voltage equation both for the positive half cycle as well as the negative half cycle. So next, the derivation of parameters. What are the important parameters that are to be derived means, what are maybe the rectifier. First we need to derive the ripple factor, and then the rectifier efficiency eta, and the next transformer utilization factor, and fourth one, that is a peak inverse voltage. Okay, one by one let us see here. So first let us derive the ripple factor. As you know, the ripple factor formula is root over Vrms by Vdc whole square minus 1. Okay, this is a formula. So here we need to derive Vrms, we need to derive Vdc. Okay, in order to calculate the ripple factor of full wave rectifier. Okay, so already you know about the formula of the average voltage value, that is I am writing here once again, Vdc is equal to, okay, 1 by 2 pi integral 0 to 2 pi V naught of t d of omega t. Okay, V naught of t d of omega t. V naught of t, we can write it as V naught of omega t d of omega t. This is the average voltage value equation. So here let us separate this into two parts. 1 by 2 pi, I am taking common, 0 to pi V naught of t d of omega t plus integral pi to 2 pi V naught of t d of omega t. Okay, so we observed in the last discussion about the operation, V naught of t value will be equal to Vm sin omega t whenever the omega t is in between 0 to pi. That means during the positive half cycle, the V naught of t, we need to take the value as Vm sin omega t. Similarly here, whenever omega t is in between pi to 2 pi, once again V naught of t value will be equal to same Vm sin omega t. Okay, so here I am writing the equation like this. As you can see, 0 to pi Vm sin omega t d of omega t plus integral pi to 2 pi, also V naught of t value will be Vm sin omega t to d into d omega t. So in the same value will be defined for the two integral parts, 0 to pi and pi to 2 pi. That's why here I am writing the equation like this. So 1 by 2 pi into 2 into integral 0 to pi Vm sin omega t d of omega t. Okay, so same value is defined in two cases. So that's why here I am taking 2 into individual parts. I am taking, instead of two integrative parts, I am taking one part and I am multiplying with 2. Okay, so here 2 into integral 0 to pi Vm sin omega t d of omega t. So here this 2 and this 2 will be cancelled, and finally you will be getting this equation. So finally Vdc is equal to 1 by pi integral 0 to pi Vm sin omega t d of omega t. So this becomes, so if you take Vm outside, Vm by pi, so integral sin omega t, what is the integral sin omega t d of omega t, will be getting minus cos. So that's why here minus cos omega t, whenever you apply the limits of integration, so cos pi means you will be getting minus 1. Cos 0 means 1. So if you go for the calculations, you will be getting 2 Vm by pi. So VDC is equal to 2 Vm by pi. If I want the value in current, that means IDC. So simply I need to divide with RL. So VDC upon RL. RL is a load resistance. So VDC value is 2 Vm by pi into RL. So we'll be getting this 2 Im by pi R in terms of voltage, 2 Vm by pi RL. So next VDC can be written as 2 Vm by pi. Whenever you consider the resistance of the diode as well as the transformer secondary winding resistance RS, the equation can be rewritten like this: 2 Vm by pi minus the drop across these two resistance. When you consider, one is RS, second one is RF. RS is a forward resistance of the diode. So we can write the equation like this. Similarly, the current equation IDC, VDC by, earlier it is VDC by RL. Now we need to consider the resistance of the secondary winding as well as the forward resistance of the diode. So the equation will be changed like this: 2 Vm by pi into RS plus RF plus RL. Okay. So next we need to derive the VRMS. So same thing here. Once again, let me write the VRMS formula here. VRMS means root mean square. So root will be there, mean will be there, and square also will be there. Okay. So here I am writing 1 by 2 pi integral 0 to 2 pi. So here V naught square of t d of omega t. So this is, and also root will be there like this. Okay. So square is there, mean value is there already, and root also will be there. This is a formula. So same thing here. When you observe the operation, the output voltage V naught t will be equal to Vm sin omega t whenever omega t is in between 0 to pi, as well as whenever omega t is in between pi to 2 pi. Okay. So that's why here I written in the same as in the earlier case. That's why here this 2 will be cancelled with the 2 and same value is defined. That's why 2 into integral 0 to pi Vm square sin square omega t. So that's why here we can see here 2 will be cancelled and the formula will be like this: VRMS is equal to 1 by pi integral 0 to pi Vm square sin square omega t d of omega t under root. So if you go for the calculations here, sin square theta can be written as 1 minus cos 2 theta by 2. So whenever if you go for the integration of the cos, you will be getting sin n pi will be always equal to 0. So that's why here only the first term will be getting 1 into d of omega t. If you apply the limits, you will be getting pi minus 0. So if you go for the calculation, you will be getting, treat it like an exercise. Here simply observe here sin square theta is there. Sin square theta can be written as 1 minus cos 2 omega t by 2. So if whenever you segregate that equation, 1 by 2 minus cos 2 omega t by 2. So if you go for the second part integration, cos will be getting sin n pi always it will be equal to 0. That's why the second term can be ignored. Only the first term is there. What is that? First term is 1 by 2. So 1 means if you 1 into d of omega t, you will be getting omega t. If you apply the limits, pi minus 0. So you will be getting finally Vm by root 2. So VRMS is equal to Vm by root 2 and VDC is equal to 2 Vm by pi. That we need to consider. So we know the value of VRMS and we know the value of VDC. If you calculate those values, you will be getting the ripple factor. So ripple factor you can observe here 0.482. 0.482. And one more thing is this particular ripple factor can be written like this: VAC by VDC, the ratio of the AC voltage by the DC voltage. So observe here the ripple factor of half wave rectifier we got the value as 1.21. So VAC by VDC is greater than 1. That means VAC is greater than VDC. So the AC components that are contained in half wave rectifier output are more when compared with the DC components. That shows the that shows the property of the half wave rectifier. It has got a poor regulation. Why? Because AC components are more when compared with the DC components. Okay, we will be expecting the rectifier output to be AC free. That means a pure DC output voltage we will be expecting. But if you observe the half wave rectifier, AC components are more when compared with the DC components. Now, we got the value of ripple factor of full wave rectifier as 0.482. 0.482 means it is less than 1. That means AC components are less when compared with the DC components. That's why we can say full wave rectifier is the best one as far as the rectification is concerned. So next factor, next parameter to derive is the rectifier efficiency. You know the formula, rectifier efficiency is equal to PDC by PAC. PDC means the DC power output collected across the load RL, and AC, the AC input power provided to the rectifier. Okay. So the formula we can write PDC as VDC square by RL. That means power is equal to, we can write it as V square by R or I square into R. If you know the voltage, we can use the first equation. If you know the current, we can use the second equation. So here we are writing in terms of voltage. That's why VDC square by RL, and here VRMS square by RL. So VDC value know 2 Vm by pi, and VRMS value know Vm by root 2. Okay. So you'll be getting, if you go for the calculation, you'll be getting 0.812. If you talk in terms of percentage, the percentage will be 81.2. Okay. So the maximum efficiency of full wave rectifier is 81.2. This is about the rectifier efficiency. Next is the transformer utilization factor. Quite a complex one here. So earlier in the half wave rectifier, directly we calculated by making use of formula. That is the formula of TUF, that is the transformer utilization factor, is PDC by PAC rated. Okay, PAC rated. Okay. So by taking this formula into consideration, we calculated the TUF value, that is the transformer utilization factor of a half wave rectifier, as we got the value as 0.287. You can refer back if you want. Okay. The TUF value of half wave rectifier is 0.827. Okay. Kindly keep in mind about this value, that will be used later. So here the TUF value of full wave rectifier. If you observe the full wave rectifier circuit, let us go to the circuit diagram. As you can see here, so this is a primary winding and this is a secondary winding. So while calculating the value of TUF, so we need to consider the primary as well as secondary. The primary winding TUF you need to calculate, and the secondary TUF you need to calculate, and you need to go for the average of 2. Okay, that is the process of calculating TUF. So as you can see, the primary winding, as you can see, it is driving two halves, upper half and lower half. Two halves which are like a half wave rectifier. That means it is driving two half wave rectifiers. So that's why here the TUF value of primary we can write directly. I am writing directly here the TUF of the primary winding of full wave rectifier, which is driving two half wave rectifiers. That's why here, what is the value you got? 0.287. I am writing directly 0.287. Okay, and the value will be, you will be getting 0.574. Okay, so this is about TUF of primary. Now let us calculate the TUF of secondary. So what is the formula? We need to go for the formula here, PDC by PAC rated. That means rated means the rated voltage rating of secondary winding, that depends this particular formula. So PDC, what is the formula here? So PDC I am writing in terms of current IDC square into the load resistance RL. Okay, that is about PDC. And PAC rated, So PAC rated means first we need to write the voltage rating of the secondary of the transformer. So we need to take it granted, I can directly write it as Vm by root 2 into IRMS value of full wave rectifier. So what is IRMS value of full wave rectifier? That means IRMS is equal to, what is the value we will be getting? Im by root 2. Okay. So this Vm by root 2 is a rated value of secondary, and this current value is nothing but IRMS value of full wave rectifier. Just we derived now. So I am writing the value as Im by root 2. Okay. So if you write the values here, let us use this particular line. So IDC value, what is IDC value got? 2 Im by 5 whole square into RL upon. So this Vm I am writing in terms of current. So Vm I am writing it as Im into RL. Okay, I am converting this voltage into current, right? By root 2 into Im by root. So Vm I wrote simply Im into RL by root 2 into Im by root 2. So as you can see, RL is there both in the numerator and denominator, and here Im square is there. Im square will be cancelled, and if you go for the calculation, you will be getting 8 by pi square. 8 by pi square. So if we calculate the value of pi here, 8 by pi square, you will be getting the value as 0.812. So this is a primary TUF value and this is a secondary TUF value. So finally the TUF of full wave rectifier can be written as the average of two TUFs. That means TUF of primary plus TUF of secondary by 2. So you will be getting, this is 0.574 plus 0.812 by 2. So you will be getting, finally you will be getting 0.693. So finally the TUF value of the full wave rectifier is 0.693. Okay. Next, peak inverse voltage. So what do you mean by peak inverse voltage? Peak inverse voltage is the reverse voltage, maximum reverse voltage the diode can withstand under reverse biasing of the diode. Okay. So the maximum reverse voltage the diode can withstand under reverse bias, that we call it as a peak inverse voltage. In the half wave rectifier, we had seen that peak inverse voltage of half wave rectifier is Vm, where Vm is a peak value of AC input voltage. Okay. Now let us see the full wave rectifier here. This is a circuit diagram. So this is a center tap transformer. Okay. This is a center tap transformer. So during the positive half cycle means whenever omega t is between 0 to pi, what is happening here? The diode D1 is conducting and diode D2 will be reverse bias. So here I need to check the peak inverse voltage of diode D2. Okay, I need to check the maximum reverse voltage that this diode is able to withstand whenever it is under reverse bias. As you can see, during the positive half cycle, D1 is forward bias. So whenever it is forward bias, it behaves like a short circuit and a current will be flown in this direction. So a voltage will be developed across this resistance, load resistance, let it be Vm. Okay. Peak value I am writing here. So whenever D1 is forward bias, current will be flown through the diode and the current will be flown through the load resistance RL, by which a voltage Vm will be developed across the load resistance RL. Now, what about the diode D2? So here, before going for the operation here, so here the Vm value will be there and here the Vm value will be there, the peak value of the AC input voltage. So because this diode is forward bias, whatever Vm is there here, provided input voltage, peak value, that will be absorbed across the load resistance RL. Why? Because D1 is forward bias. So Vm is absorbed here. And here already here the provided input voltage once again for the lower half also it is Vm. So the diode is D2 is under reverse bias. So the Vm, the value must be withstanded by this diode D2. Why? Because it is reverse bias. So already it is withstanding Vm. Already if you observe the loop equation here, already across this load resistance RL, Vm is there. So Vm plus this provided input voltage Vm. So the total voltage that has to be withstanded by this diode D2 must be Vm plus Vm. Okay, that will be equal to Vm. So Vm is the provided input voltage for this lower half of the center trap transformer, and already Vm is absorbed across the load resistance RL. Why? Because D1 is forward bias. So the total voltage of this loop is Vm plus Vm, 2Vm. So that's why the diode D2 has to withstand a total voltage of 2Vm in its reverse biasing state. So that's why it is called as a peak inverse voltage of the full wave rectifier. So the peak inverse voltage of full wave rectifier is 2Vm. The peak inverse voltage of half wave rectifier is Vm. Okay. So this diode D1 is forward bias, by which a voltage will be developed across the load resistance RL. So that's why here the voltage here must be Vm, and here the provided input voltage for this center tap transformer lower half must be Vm, peak value of AC input voltage. So Vm and this Vm, total voltage in this loop is 2Vm. So that has to be withstand by this diode D2, which is in reverse bias. So total voltage will be equal to 2Vm, which is called as a peak inverse voltage. So let us recap the things. First, I discussed about the operation of full wave rectifier, and second, I derived the parameters. What are the parameters? Derivation of. So first, I derived the ripple factor. Okay, and next I derived the efficiency, rectifier efficiency, and then I derived the transformer utilization factor TUF, and finally we discussed about the PIV value, peak inverse voltage or peak reverse voltage. Okay, so with this I conclude my presentation.